So those who are online are able to hear me?
Yes, sir.
Yes, sir.
Okay. எதுப்பா ஏதோ ஆன்ல இருக்கு வைஃபையா வைஃபை ஆன்ல இருக்கா ஆ can sit this side. I want this row to be in the வேணுமா இந்த bench. I want this bench to be. Can you come this way? அந்த லைட் அடிக்குது. நான் வைஃபை கட் பண்றேன். அது தெரியுதா? ஜூம் அவுட் பண்ணு ஃபுல்லா. வைஃபை ஆன் பண்ணு. வைஃபை. Shall we proceed? So what were the concepts we discussed yesterday? We saw what are the force experienced by current carrying conductor placed in external magnetic field. Similarly, we also saw what are the force acting between two parallel current carrying conductors, right? So having said that, the next topic that we are going to see is what is going to be the So the next topic that we are going to see is what is going to be the torque experienced by a current carrying loop placed in external magnetic field. Okay, so this is where you need to be careful. Okay. So here if you observe, when I talk about a current carrying loop and torque, right, it is a concept which is similar to what happens when an electric dipole is placed in external electric field. You remember that concept? So when you take electric field and you place a dipole in external electric field, what will happen to it? It will experience a torque of magnitude P vector cross E vector or P sin theta. You know this, right? So the concept is exactly similar, right? But the only difference is whenever you speak about torque placed in any field, I'm not talking only about magnetic here. So listen to this concept very clearly. whenever you want any material to experience torque in the presence of any field, that material is supposed to be a dipole. So if you're placing it in magnetic field, it will be a magnetic dipole. If you're placing it in electric field, it will be an electric dipole. That's the only difference. So are you able to understand? Who's Akhil's sister here? Both of your Akhil's sister. Okay. So what was I telling? Yeah. So when you place a material in external magnetic field, you need to place a dipole. That can either be a electric dipole or a magnetic dipole. So if you look at the topic again, right, we only told torque experienced by current carrying loop placed in magnetic field. So first thing that we are supposed to prove is that a current carrying loop is a magnetic dipole. Okay. So what we'll do for that is, if I take a loop like this, so when I say a loop, right, it is not necessary it needs to take only a square shape or a circular shape. It can be of any irregular shape. The only thing is it is supposed to be a closed surface. Am I clear with this point? So if I take the current to flow in this direction, let's say the current is flowing in the clockwise direction in this scenario. Now tell me one thing, due to this clockwise current, what is going to be the direction of magnetic? You already know this. When you talk about a current carrying conductor, how are you going to find the direction of magnetic field? Apply right hand thumb rule and tell me. So it is into the plane. If you take due to each surface, it is into the plane. Means this kind of a current flowing in a clockwise direction is able to receive the magnetic field lines. Am I right? So which pole has a tendency to receive the field lines? Which pole has a tendency to receive? If you take a bar magnet, for instance, if I have this as north pole, this as south pole, the magnetic field is going to be from north to south outside the magnet, and inside it is going to be from south to north. So which pole has a tendency to receive the field lines outside the magnet? South. So when the current is flowing in clockwise direction, since the magnetic field is into the plane, the pole that you're actually facing is a south pole. It's a south pole. Okay. Similarly, if you go to the back of the board and see, the same clockwise current will appear to be in anti-clockwise. See, for example, if I see from this direction, if the current is flowing in the clockwise direction, when you see from here, it is clockwise direction. So remember, the current is going in this direction. Okay. Remember this finger. I'm taking only the top surface. At this point, the current is going in this direction. If I exactly flip it and show it, what direction is this? Anti-clockwise means for the same loop, if you see it from one side, it is going to be clockwise. Exactly on the back side, it will be anti-clockwise. So when I go to the back of this board and observe, what will happen? That will act as the pole which is actually emitting the field lines. So what is happening here? Observe. So this is the direction of current according to the diagram. So current is flowing in the clockwise direction. So when this is going to act as a south pole, means when this is receiving the field lines, what is coming out of my hand? The field lines are coming out of my hand from which side? So if I take my hand itself, the palm which you are able to see, right? The palm that you are able to see is receiving the field lines. The side where I have the knuckles is actually pushing the field lines. In the sense, this is going to be the one which is receiving, this is the one which is emitting. So what pole is this? So what pole should this be? Right? Means for the same loop on either side of it, you have both south and north, as a result of which it is acting similar to a bar magnet. So that is why, since you have both the poles present in it, you call it as a dipole. What dipole is this? It's a magnetic dipole. So one important point that I want you all to register in your mind is, every current carrying loop acts as a magnetic dipole. So every current carrying loop acts as a, so every current carrying loop, if you see this word itself, the first thing that should come to your mind is magnetic dipole. Is that point clear? Right? So we didn't go to the main topic yet, but I wanted to explain why a current carrying loop is actually a magnetic dipole. Do you guys understand? Right? So just make a note of this. So the conclusion is every current carrying loop will act as a magnetic dipole. Now what we are going to do is, you will take this current carrying loop and place it in the presence of external field. Okay. So what are the two things that you need here? So what are the two things that you need here? One is you need the external field. And the second is you need a dipole based on it. So here what I'll do is I'll take the dipole to be rectangular itself. Okay. So I'm going to use some concepts and terms. So concentrate. So current is flowing in the clockwise direction. And what is the value of this magnetic field? It is B. Is that point clear? Okay. And let's say that the value of the current here is I. And this side, let it say it has a value of B. And this side has the length to be A. Okay. So what I'll do is, can I say that this particular loop is made up of 4 straight current carrying conductors, right? So if I take this to be 1, 2, 3, and 4, right? Now my question is, I'm going to break it into 4 individual parts and observe what is the force experienced by each side, right? What am I calculating? I'm only calculating the force. After force, I'll come to the concept of torque. Because you need to remember one thing. What is responsible for linear motion? If you want an object to move in a linear motion, you need to apply force. If you want it to rotate, you need to apply torque. So we didn't come to rotation yet. We'll only see what is the force applied on it. So on the first conductor, tell me what is going to be the force. So I'll erase this. Yeah. So on the first conductor, what is going to be the force? We know that F is equal to BIL sine theta when you take it in terms of magnitude. So what is the value of B? It's B only. What is the value of I? It is I only. What is the value of length of this conductor? It is small b. Right. And the next question in this case is, what is the angle between I and B? It is 90. So I'll take it as sine 90, which is going to be 1. So it is going to be B into I into the small b. Right. Right. It's bib. Right. Okay. What about the second one? What about the second conductor? So F will be equal to B. B is B only. So the same formula is applicable. F is equal to BIL sine theta. I'm not writing it again and again. So BIL sine theta, B is B only. I is I. L is A. Sine of how much is the angle? It is 0. So sine 0 is going to give you 0. The meaning of this conductor is not experiencing force at all. Similarly, if I take the third conductor, for third conductor again, so I'll call this as F1, F2, and let me call this as F3. F3 is going to be B into I into B into sine 90. So how much is the answer going to be? Same thing, BIB. Okay. What about the fourth one? F4, it will be B into I into A into sine of sine 180. Answer is going to be 0. So second conductor and fourth conductor are not experiencing force at all. Right. But what is happening to the first and the third? They are experiencing force. Right. They are experiencing force. But the question is, in which direction are they experiencing force? If I look at F1 and F3, I wrote only in terms of magnitude. So if I write it in terms of vector quantity like this, then what is the direction of force experienced by the first conductor? Apply the Fleming's left-hand rule. Forefinger in the direction of field, central finger in the direction of current, and thumb in the direction of force. So forefinger in the direction of field. Central finger adjusted so that it comes in the direction of current, and extend the thumb. The thumb is pointing into the plane. So in this case, the force experienced by the first conductor is into the plane. Means this conductor left to itself will start moving into the plane. So what about this one? So this is the field, this is the direction of current, extend the thumb. So it is out of the plane. So F3 is going to be in such a way that this force will pull the third conductor towards us. So the first conductor is being pushed away from us, the third conductor is being pulled towards us. So as a result of which, tell me, what is going to be the net force acting on the system? Net force is 0. Why? Because they both are of equal magnitude but exactly in opposite direction. So it gets nullified. So force is 0. Now the question is, how is the torque defined then? And how will the system even rotate? Then why are we even talking about torque? There is no point. When force is 0, then how can torque be produced? Both are independent. Torque and force are different. Not dependent. We write torque is equal to RF sin theta, no? The force is there, no? Then how is torque independent? What is the formula for torque? Torque is equal to R vector cross F vector when you write it in terms of vector, or you write it as RF sin theta. Then how can you say torque and force are independent? This I've told you many times. So thing is, if there is a displacement, then force can't be 0. So what will happen is, this conductor is being pulled inside. Sorry, this is being pushed inside and this is being pulled outwards, right? These two conductors which are at the top are actually acting as a support system. Meaning, this is trying to move into the plane, this is trying to come out of the plane, but what are these connections doing? They're not letting each of them to move. They do not have translational motion, rather they have rotational motion. So that is why the torque comes into picture, right? So this I have explained once. If you remember, if you take this water bottle, right? Remember, I'm repeating it again. How are you going to open this? So let's say this is one force. Okay, what is the concept you're using? You're actually using friction, right? You're going to hold it, right? Like this, if I try, it is not opening. Like this, if I try, it is not opening. But if I use both the fingers and rotate it, I'm able to open it. So what is each finger doing? This finger is applying a force in this direction. The thumb is applying a force in this direction. So the force net value is 0, but still there is a torque acting on the system. So these kind of forces where they have equal magnitude and opposite direction are called as couple, C-O-U-P-L-E. Okay. So this is the exact concept used to drive also. You take a steering wheel, what do? One hand pulls it down, the other hand pulls it up. Same logic. Okay. So two forces of equal magnitude acting exactly in the opposite direction, but they produce what? The net force will be 0, but they'll produce net torque. You understood here? Though the net force is 0, it has nothing to do with torque because the forces are putting the system into rotation. The system would have not rotated had these two wires not been there. That is why you need a closed system. Had second and fourth conductor not been there, this would have been a conductor, this would have been a conductor. This conductor will experience force, this conductor will experience force, but as a system, it will not rotate. So that is why for any system to rotate, you need a loop. You're able to understand? So when you talk about rotation, the first thing that you need to define is the axis of rotation. So when it starts revolving, observe if this is the dipole, let's say it is revolving like this, right? When it is revolving like this, it is rotating about this axis. Are you able to understand? So it is rotating about this axis where the distance from each force to the axis of rotation is a/2. Because it's a symmetrical shape, the axis of rotation will exactly pass through the center. So it will be a/2, right? Now I'm ready to apply this formula of torque is equal to Rf sin theta. So what does that Rf sin theta mean? R is the distance from the point of application of force to the axis of rotation. Okay, give me a book. Just give me some book. You know, so how are you going to open this book? You hold it here only, no? You don't know. Will anyone do it like this? Why don't you do it? Why don't you even think of it? Suppose you wanted to open from the center, will you try to open it like this? Or this is easier? Why? You're doing it without your knowledge. Why? Same logic. Distance is more, the force that you need to apply is less. That's what it says. Meaning, if I need to produce a torque of from here, let's say I need to produce a torque of tau. Okay, if I produce it from here, since the distance is more, I need to apply less force. If I need to produce the same tau from here, distance is less, so I need to put more effort. You're able to understand? So you're able to visualize what is this? What is this called as? This is the axis of rotation. From the axis of rotation, more is the distance, lesser is the force that you need to apply. So when I talk about this Rf sin theta, R is the distance from the point where I apply the force till the axis of rotation, and theta is going to be the angle between R vector and F vector. Okay. So having said this, if you observe, what is the torque experienced by the first conductor? It is going to be, what is the distance? For the first conductor, what is the distance from here till here? A by 2. So it is going to be A by 2 into, what is the force that you have applied? B into I into small b into sine of, what is the angle between, okay, what is the angle between the force and the distance? In this case, the force is into the plane, the distance is along the plane. So they are 90 degrees exactly. So it is going to be sine 90. What will be the answer here? It is going to be BIAB the whole divided by 2 into 1. Makes sense? So again, I wrote it only in terms of magnitude. I didn't write it in terms of direction. Now, if I take this as torque 1 in the vector form, then observe what is going to happen is, since the force is acting into the plane, when you see from here, let's say your eye is here. When you see from the top, in which direction will it tend to rotate? In which direction will it tend to rotate? Clockwise, right? So when it is going to be clockwise, remember clockwise moments are always negative. Anti-clockwise moments are always positive. Again, the same logic. If you want to open this water bottle, in which direction do you rotate the cap? Anti-clockwise. So how is the cap coming? Towards you. Anything towards you is positive. Away from you is negative. Okay. So if at all you forget, I am sure that you will have a water bottle in your hand. You can think with that as an example. Okay. So in this case, what is happening when you see from the top, the coil is rotating clockwise. So it is going to be into the plane. Right. So it is going to be negative. It is going to be negative. What that negative is, I'll tell you. Right. It is going to be a negative torque. Similarly, what is the torque experienced by the second conductor? It is 0 because there is no force at all. What is the same is going to be the torque experienced by the fourth conductor? Then what about the torque experienced by the third conductor? So it will be A by 2 into B into I into B into sine theta, that is sine 90, right? Force is outward, perpendicular distance is A by 2. So R is A by 2 into F is BIB into sine 90. What is going to be the direction? Is it going to be positive or negative? If it is positive, then torque will also get cancelled. All my energy is waste. There is no concept of torque then. So if it has to rotate, what should happen? I told you about the example, no? So what is happening? Both these forces are trying to put the system into the same clockwise rotation. So see from the top, no? See, if you have the conductor like this, okay, if you apply a force like this, right? Look at this finger. This is F1. Okay, I'm trying to pull it towards me. In which direction is it rotating? When you see it from the top, clockwise, no? Same logic. So is this clear now? So what is going to be the net torque acting on the system? Net torque will be equal to torque 1 vector plus torque vector. So the net torque is going to be negative only. I didn't tell you what that negative is yet. Okay, I didn't tell you what that negative is. Observe, it is going to be B into I into AB divided by 2 plus B into I into AB divided by 2, and the overall direction is going to be negative. Okay, so the sum of these two is going to give us B into I into AB, right? Now listen to this carefully. This AB is there, no? What can you call that AB as for this shape? A into B. It is going to be the area of this loop. So can I write this as B into I into A? Can I write it like this? B into I into A. Now listen to this. This is going to be the torque experience when there is one turn. If there are n turns, right? If there are n turns, then the torque experience will be equal to n into I into A into B. N into I into A into B. The reason why I clubbed this IA is because this N into I into A is given a name called as magnetic dipole moment. And this B is obviously going to be the magnetic field. If you compare it with the already known expression, which is PE sine theta, if the value of theta is 90, what will happen? It will be P into E, no? So instead of electric dipole moment, you have magnetic dipole moment. Instead of electric field, you have magnetic field. The expressions are similar. Are you able to understand? So when you place any dipole in any magnetic field, the expression for torque will come out in such a way that it is always a product of dipole moment and that field. Are you able to understand this point? So this P sine theta is there, no? Instead of P, you have magnetic dipole moment. Magnetic dipole moment is represented by the symbol capital M, right? Capital M, and magnetic field is represented by B. So this is going to be the torque experienced by this system in this case. If I have to write the general formula, right? If I have to write the general formula for it, then it is going to be MB sine theta in terms of magnitude, where theta is going to be the angle between, here what is theta? Theta is the angle between dipole moment and electric field. Here what is that theta? Angle between magnetic dipole moment and B vector. Simple, you are able to connect both, right? That is how it works. Next is, if you write it in terms of vector quantity, then it will be M vector cross B vector. Like how you write P vector cross E vector, here it will be M vector cross B vector, and this expression is to be remembered. So whenever somebody asks you what is magnetic dipole moment, what are you going to say? It is going to be the product of the number of turns, magnetic dipole moment. It is a product of number of turns, current flowing through the loop, and the area of that loop. So N into I into A is what is called as magnetic dipole moment. Right? Are you able to relate both the concepts? Right. So one last point that I need to explain is about this negative. Right. So tell me one thing. Look, take the water bottle example. When you close the water bottle cap, in which direction is it traveling? Downward, right? So what is happening here is, when you see from the top, it is rotating clockwise. No, means the system, when you see it from the top, will appear as if it is flowing in the downward direction. So that minus sign that I wrote there, the minus sign that I wrote here is actually negative j cap. It is minus j cap, means the whole system will rotate in the clockwise direction and come in the minus j cap direction. So this minus j cap is only to this particular diagram. So don't generalize it everywhere. Suppose I had taken a situation where the current had been in anti-clockwise direction, then I would have got plus j cap. Okay. So I hope you could understand everything that is related only to this scenario, right? So the important point that you need to remember is it is mb sine theta or m vector cross b vector. So this is the expression we try to derive. Is that point clear? Yeah. So just make a note of it. Yes, it will appear as if it is moving downward. It should move actually. But something will hold it. Shall I proceed to the next slide? All right.
Sir, you're not audible, sir.
Yeah. For those who are online, observe. Right. So the point is at the center, right? And here it is at the zero is at the center here, and here the zero is at the end, because this is a measuring device and this is a sensor. So it will only detect and tell whether current is flowing through it or not. Right? So now if I take, you all know what this is, right? You have a battery eliminator which is going to supply the power. So if I switch on the battery eliminator, you know that the red is used for positive and this is used for, the black is used for negative, right? So when I take this and connect it across the galvanometer, observe what is going to happen. I'm not going to connect it. I'm just putting the wire inside. I'm putting the wire inside and I'm putting it here also. So when I put it inside like this, and how much is the voltage? Yeah, I kept it at 2. Observe what is happening to the galvanometer. The galvanometer's deflection is completely to the right. Right. Now, what I'll do is, I'll just reverse the polarity. Means I'll take this blue and put it in the black and the red into the red. That is, I'm just interchanging the polarities. Observe what is going to happen. It is going to the left. So it doesn't mean that the current is clockwise or anti-clockwise, nothing like that. So it is only trying to tell us, if you connect the positive to the positive and negative to the negative, the galvanometer shows a deflection to one of the sides. If you reverse the polarities, the direction of current is getting reversed. As a result of it, the pointer will also turn in the opposite direction. Are you able to understand? So the important question is, how is this pointer working in the first place? It is rotating. So if something has to rotate, what is needed? If something has to rotate, torque is needed. So who's producing the torque in this? So what should happen here is, this is where the logics are supposed to get connected. What was the previous topic that we discussed? Torque experienced by a magnetic dipole placed in external magnetic field, right? Means inside this, you should have magnets. What should you have? Inside this, you should have magnet and you should have a coil. Whenever current is passed through that coil in the presence of that magnetic field, what will happen to it? It will start experiencing torque. That is why it is rotating. The same is the principle used in an ammeter and voltmeter also, because they are also measuring devices only. So what will be present inside? For anything to rotate, what is needed? External magnetic field and you need a current carrying coil, right? So inside this, you will have magnets, external magnets, and current carrying coil, which is connected to this pointer. And due to the torque experience, the pointer is rotating in either of the directions. That is why I told you in the previous case, if you remember, if the current, when you're looking at it, if it is taken in clockwise direction, the torque experience was in the downward direction. If you change it to anti-clockwise, it would have been in the upward direction, right? The same logic. So when I took the direction of current to be connecting positive to this and negative to this, the pointer went to the right. When I reverse the polarities, what happened? I changed the direction of current, as a result of which the pointer also rotated in the opposite direction. So are you getting a validation from this? So this is a device which works on the principle stating that a coil, a current carrying coil placed in an external magnetic field experiences torque. Are you able to understand this? Right. So having said this, we'll get into the theory part. ஸ்டார்டிங் ரெக்கார்ட் ஆகல, வாய்ஸ் மைக் ஆஃப் வச்சிட்டேன். பரவாயில்ல விட்டுறப்பா, அப்புறம் பார்த்துக்கேன். அதுல இருக்கும், அது நாய்ஸ் கேன்சலேஷன் அதை போட்டு பண்ணிட்டு. So did you understand? Right? So basically, when you talk about a moving coil galvanometer, right? When you talk about a moving coil galvanometer, it is a device used to detect. This is the most important point. It is used to detect the current in a circuit. It will not measure the value. But the question is there a possibility that a galvanometer can be converted to an ammeter and voltmeter? You can do that. Because as I told you, galvanometer, ammeter use the same principle. But only thing is, this device, the galvanometer, is designed only to detect current. Means it is only a sensor. If I have to give you an idea of what a sensor is, so you go in a lift, right, where there is a door that is getting automatically closed. Let's say you're in a hurry, the door is getting closed, you want to open it. What will you do? You just put your hand and take it out. No. So what is happening there? There is some sensor trying to tell that there is an object trying to interfere, due to which the microcontroller will start pushing the doors away. So it is sensing, no, when your hand is going in. If it is not working, what will happen? I don't want to tell that. Okay, you know that. So in a similar way, this is also a device which is only going to say whether current is flowing or not. It cannot tell you what is the value. Okay. Second point is, whenever in a lab, right, if they give you a galvanometer and let's say you're trying to do the experiment, finally you're not able to find something called as null point. Because you remember in Wheatstone bridge also, balanced Wheatstone bridge also, we discussed it. What should the galvanometer reading be? It should be 0. So that is called as balance point, right? You'll be doing that in experiments like meter bridge and potentiometer, right? You need to find the balance point. Okay. So if you're not getting the balance point and the pointer is showing only one side, even before you proceed with the connections in the circuit, right, you need to first check whether the galvanometer is working or not. How will you check it? Like how I did it now. If you connect the positive to this and negative to this, if the deflection is to the right, if you reverse the polarity, the deflection should go to the left. Sometimes you will have a galvanometer where, however you connect, you show the deflection only one side. Means it's a spoiled one. You have to get it replaced immediately before you proceed. Okay, that is one test that you need to do in the lab. Okay, that is why I'm saying it is only used to detect the presence of current. And the next question is, what is the most commonly used one? Right, the most commonly used one is a moving coil galvanometer, and it is named because it uses a current carrying coil that rotates. Obviously, right? So the pointer is there. The current carrying coil placed in the external magnetic field is putting it into rotation. It is moving, no? The coil is moving. That's why it's a moving coil galvanometer. Right? So why is it moving? Because it has placed the presence of magnetic field, due to which it will experience torque. So you understood this, right? Now the question is, whenever you are learning about any device, right, the first thing is you should know what the device is. Second is you need to understand what is the principle on which the device is designed. So what is the principle on which it is designed? Exactly the name. What is it? A current carrying coil placed in a magnetic field experiences torque. This is the principle. Okay. A current carrying coil placed in magnetic field experiences something called as current dependent torque. Why we call it as current dependent torque is because you have the formula as NIAB. It is dependent on current. So it is a current dependent torque which tends to rotate the coil and produce angular deflection. Right. Now, having said this, how is the construction of this particular device going to be? Meaning, I have some screws here. Right. If I'm able to remove it, right, I go deep into it, I'll be able to find a circuit of this format. This is the construction of it. So what is there? Basically, there are two magnets. Right. What are the magnets? They're going to have, they're two poles basically, North Pole and a South Pole. If you observe, they are not completely in a rectangular shape. They are in a curved shape. Basically, they take concave shape. Right. They take concave shape. The reason for the concave shape in this particular magnetic structure is because we want to produce something called as radial magnetic field. What are we producing? We produce something called as radial magnetic field. That is why the field lines are like this. You're able to see the black color ones are the field lines. Inside which, what is present? There is a coil. You're able to see these pink color lines, the three lines that are there. This is the coil. So in the presence, so when you look at, this is actually the top view. When you look at it from here, this is how it is going to look. Whereas when you look at it from the side, this is how it is going to look. So this coil is there, no? This coil which is wound around a cylindrical shape is there, no? That cylindrical shape is basically a soft iron core. It is a core on which the winding is done. It is the one which is holding the coil. Okay. So when you look at it from the top view, it will appear like this. Because when you see it from the side view, you will be able to see the rectangles. Whereas when you see from the top, you will only be able to see those lines. That is why these lines. So this coil is the one which is experiencing the torque. When will it experience? Only when you pass current, or else it will not, it will be at zero only, like how you saw it, right? Now the next question is, okay, it is experiencing a torque. Okay, let's say that this pointer is coming and standing here. That will happen as long as you pass the current. But when you remove the current power source, what should happen to it? It should say that there is no current, so I'll come back to my original position. Who's bringing it back to the original position? So there should be someone who's telling it and trying to bring it back to original position. No, that is done by this SP called as spring. So it is basically called as hairspring, which is in the form of a spiral winding. It will have spiral windings. Due to that spiral winding, it will come back to the original position. The pointer will come back to the original position as soon as you remove the external magnetic, remove the current source. Is that point clear? Am I clear till this point? Okay. So this is the basic construction. This is the basic construction. If you look at the same thing in this side, you're going to have this hairspring, which I told you, right? You have a soft iron core cylinder. Jewel bearing, you need not worry about. So you have the terminals, right? You have the terminals here, positive and the negative terminal. Then you have a pointer and this magnet, right? From here, it is appearing as if it is two magnets, right? But actually there is one magnet, which is like this, and the ends are cut in the form of a concave shape. Because you take any magnet, right? No magnet can have a monopole. Every magnet will only have a dipole. So you can have an electric monopole, but you can never have a magnetic monopole. You only have a magnetic dipole, because magnet always exists in the form of a dipole. So that is why it is a single magnet. Whereas when you see from this side, it appears as if there are two magnets. Am I clear with this construction? Right? So this is the one which is given in your textbook. This is for your additional reference. Right? Now, having all these things in mind, let's try to understand how this particular device is going to work. Okay. So I'll tell you. Yes. Now, as soon as current is passed, when current is passed through this device, what will happen to it? It will experience torque. And what is the torque given by? It is given by the expression NIAB sin theta, where theta is going to be the angle between magnetic dipole moment and the magnetic field. Now, I want to stress on one point. See, we have cut this magnet in the shape of a concave to produce what? To produce something called as radial magnetic field. And this radial magnetic field's importance is, they'll ask you why a radial magnetic field is existing inside a galvanometer. Listen to this carefully. The importance of this radial magnetic field is always to maintain the value of theta to be 90 degree. Meaning the coil is being in any orientation. In every orientation, the coil is there. The angle between the magnetic dipole moment and the magnetic field due to this radial field will always be 90 degree. So when it is 90, right? Tell me logically what is going to happen. When I put 90 here, sin 90 is maximum value. So when sin 90 is maximum, can I say torque is also maximum? So what is the importance of this radial magnetic field? First thing, it always maintains the angle between the magnetic dipole moment and the magnetic field to be 90 degree, as a result of which the coil always experiences maximum torque. And what is the value of that maximum torque? When I put 90 here, it is going to give me NIAB, right? So let this be equation number 1. I hope I am clear till this step. Right? Now, if I say that this is the torque that is produced due to the current, then how much torque is going to go and sit in the spring? Because spring is also rotating along with it. No, when the pointer is moving, the spring also has to get expanded, right? So there is a torque that is stored in it. which will get restored after you remove the current carrying source or the current delivering source, right? So when is that going to happen? So when this amount of torque is generated, can I say that the torque that is there in the hairspring is going to be K times theta? So we know that F is equal to Kx when you talk about a spring, where K is the spring constant and X is the linear displacement. So force and linear displacement are related like this. In a similar way, torque and angular displacement are related like this. So here theta refers to, okay, I've used theta here also. Okay. I'll just change this part. Maybe I'll write this as here also I use theta. Okay, I'll do one thing. I'll keep this as theta. This I'll change it to some other variable. Okay. Now listen. I'll call this as K times alpha, where alpha is going to be the number of divisions the pointer has traveled. Okay. Now, can I say that this torque and this torque numerically are supposed to be the same? So Ni A into B will be equal to K into alpha. When this is the case, all that we need to do is rearrange this equation. When you rearrange the equation, if it comes out to be alpha divided by I, right? Alpha by I, this is going to be N into B into A divided by K. Right? N into B into A divided by K. If I write this as I divided by alpha, what will this be? It will be K divided by NBA. So they both appear to be the same, but they are different. So this value of alpha by I is called as current sensitivity. So what is it called as? It's called as current sensitivity because it's a sensitive device. So what is the meaning of it? Observe. I'll just give you a relevance. If I say that the speed of the object is 5 meters per second, what is the meaning of it? In each second, the object has covered a distance of 5 meters. In a similar way, if I say alpha by I, for unit value of current that you passed, I repeat it, for unit value of current that you passed, the deflection got, the number of divisions to which the pointer turned was alpha. So basically here the unit is going to be division per ampere. Means how much deflection you are able to produce in the pointer for unit value of current defines the current sensitivity. In a similar way, if I write it as I by alpha, what is the meaning of this? This is the reciprocal of current sensitivity. No, this has a name called as figure of merit. Okay. If at all you have half deflection method in your lab, right, in your practicals, you will be learning about this concept. All that you'll be calculating is figure of merit only. So figure of merit is basically ampere per division. Meaning of this is to produce, see this pointer has readings, no, 0 to 30. So this has readings between 0 to 30. Between 0 to 10, there are 10 lines. So if this pointer has to travel from 0 to its least count, that is to the next reading, how much current you are supposed to pass defines the figure of merit. So if you want the pointer to travel how much distance, it should cover only one least count. So for one least count to get covered, how much current you are supposed to pass defines the figure of merit of that particular galvanometer. Is that clear? So similar to current sensitivity, you have something called as alpha divided by V also, where V is potential difference, which is called as replace current with voltage. So it is going to be voltage sensitivity. Okay. So this is going to be alpha divided by, we can write V is equal to I into R. This R is the resistance of the galvanometer. So this will be equal to NBA divided by K into R, and this is called as the voltage sensitivity. Am I clear with this? Right. So this is all about current sensitivity, figure of merit, and voltage sensitivity. If you look at the derivation, it is only one step. All that you need to do is write the expression for torque, write the expression for torque in terms of torsional constant. Okay. So this alpha is there, which is the division. This K is called as the, it's called as the torsional constant. Like how we call this K as spring constant, here you call it as torsional constant because torsion is defined with respect to rotation. Am I clear with this? So this is all about the galvanometer. Right. Only thing is now time is less. So I would suggest you to take a pic and you please send it to me. I'll share it in the group. You can make a note of it. Want me to move? Yeah. Those are online, don't worry. I'll be mixing the video that I took today. No, I'll be mixing it with the other video that is recorded and given to you. So you'll be able to understand from there. Okay. So we can wind up, guys. Hello.
Thank you, sir.
Yeah, we can wind up.
Thank you, sir.